All right, so welcome back. Welcome back to this channel. So in the last, in the last video we have covered about Alan Turing, right? The imitation game. The paper he wrote about how can we evaluate the intelligence of machines. We have did that in the last video. In this video, we'll be doing we'll be I think using some techniques. We'll be learning about some techniques that we can do to improve our stable diffusion model. So we're learning about some techniques. I think I have already covered distillation in like one of the last videos, but I just think maybe I have to cover it again. So I think we are going to cover about how we can improve stable diffusion, right? So that is the idea. That is the main goal of this video. How we're going to learn about some technique, and there is actually a paper. I think I have closed the paper. I'll open the paper just for you. So we'll be also covering that paper also. It's a pretty new one. Yeah. If you open papers with code.com, you'll definitely. So the first paper in this time, of course, is this SGXL, improving latent diffusion models for high resolution image synthesis. So this is the paper that we'll be covering. There is not much of a change. Like they are not doing much of a change with the model, with the stable diffusion model, but the like paper. So this is the paper, SGXL, improving latent diffusion models for high resolution image synthesis. So again, we'll be for like tackling the problem of image synthesis. So how can we do that using stable diffusion? We'll be improving our models way further. So let's get started. First, I want to talk about the idea of distillation. Wait a minute. So we'll be covering first distillation. So what distillation actually is, right? I have covered this, of course, in the last video. So we use distillation to to make the model faster while generating images. So again, if in the process of stable diffusion, while we are actually generating that image, right? The input will be random noise. So in the inference time or even in the training data, so it will be some noise in the training data. It will be like number hidden up. In the inference time, it will just be pure random noise. So we'll be taking this noise, right, and we'll apply. I'm going to apply, pass that through a model, and then we'll be getting a noise function, getting a noise that we should subtract from this original image. So we'll subtract it. So we'll subtract this noise, the predicted noise by the model. So the model is actually trained to predict the noise, right? So after we subtract the noise, so we'll take the original input, this complete noise. We'll be subtracting this noise from this noise, and hopefully we'll be getting some features. We can be able to view some features, and then so this is actually called one inference steps. So one inference step is actually getting the noise and subtracting it. So this process is called one inference step. So we'll be performing this process for multiple number of times. So we'll be subtracting many noises. So we'll be predicting many noises like this, and we'll be subtracting them gradually. And so we'll be performing a lot of inference steps, and that is the idea of inference steps, right? We'll be performing these steps again and again to get that output image, right? And the problem is that whenever we are generating like high quality images, and whenever doing like complex tasks, this we might be needing many more inference steps, right? We'll be needing to perform many more inference steps, thus leading to computational complexity. So that is why we have this idea of distillation, in which, for example, let's say I just plot out all this. Let's say in the inference time, I have all of this. I have plotted out all of the images, right? So these are the images that took to, let's say, predict 9. So let's say we are building a model that to on like digit data or digit data. So we'll have lesser loss in the second type. Here we're going to have like much lesser loss, maybe 9. You can see 9 here, right? And here we'll have like minimal loss. Hopefully here we'll be like getting there. Here we'll be getting image, right? So let's say this is the training process or inference process. In the inference process, let's say we'll be taking this value and we'll be slowly subtracting something, and hopefully get to this value or this image 9, which is completely generated by the computer. So in the inference time, in fact, while we're actually performing this for high level images, for example, images such as, maybe dogs, cats, or even much more higher, or even a diverse data set, we'll be needing like much more inference steps to predict good images. So that is the idea. We'll be needing many more inference steps. So the idea is, the idea of distillation is, we will be considering this baseline model. So this is the baseline model. We'll be considering this baseline model as the teacher model. So this is the teacher model. So just like a teacher, we'll be having the data. So we'll be taking this data and we'll be using this data to train a new model called the student model. So what we'll be doing is, I'll show you what we'll be doing. So we'll be training a new student model, let's say S, right? And what we'll be doing is we'll be making the student data take this noise, or we'll be making the student model to take this noise and directly predict this frame. So we'll be having multiple frames in the inference time. In order to decrease the number of inference steps it takes for the model to predict a new image, we'll be training a new model. In order to decrease like computational complexity and the time taken by the model to predict an image, we'll be training a new model which is called the student model, and these are images that are generated by the teacher model. So this is the teacher model. We'll be making the student model predict an image for, like from taking this image as the input. We'll be taking this image as the input, right? And then the goal is we want to directly go from this to this. So we'll be performing one inference step, not from here to here, but from here to here. So we'll essentially be skipping a step. So we can actually use a simple like MSC loss function, right, to actually predict the like mean squared error between the predicted noise, or this noise and this noise, or this image versus this image. So after the inference steps, after subtracting the noises, we'll be having that image, right? We can just perform let's say an MSC between the output images, and then we could actually do that, right? We could actually do that as one training example, and we could take this as the input and predict, let's say this, taking this as the input and predict this, and we could actually do that in half number of times now, right? So we have taken like 1 2 3 4 5 6 7 8. So yeah, 8 inference steps. What we have done is we have taken a model that takes 8 inference steps to let's say predict the image or generate the image 9, to now only taking like four training steps, right? To now taking only four inference steps to like generate the image the same image 9. And that is the beauty of distillation. Again, you could add as many student models as possible, like in real world data when we're actually training like much sophisticated models, sophisticated diffusion models to predict like to generate new images, right? When you're doing it in the real data, you have multiple number of inference steps that use it to generate an image, and then this process of distillation will be really useful, because we are not even compromising on the like quality of these images. Like normally, if you look at any problem, especially in machine learning, if you want to decrease the computational complexity, you will have to sacrifice at least some performance. But here, there is no sacrifice of any performance, because we'll be like taking one frame and generating the a far more future one. And by this, yes, we'll be training a new model, but this student model will be much more faster than the teacher, and we could actually use much lesser like inference steps to predict good images with very high quality. So that is the idea of distillation. And now we'll be moving on. We'll be moving on to this paper, a very pretty recent one. We learn like all these images are predicted by stable diffusion. Again, pretty stable diffusion never fails to make us like stable diffusion never fails to fascinate us, right? These are like very good images that are actually predicted by the model. So this paper does not, as I've told you, does not make any fancy changes, fancy and massive changes, but we'll be using a diffusion model. We'll be building a diffusion model. We'll be updating the architecture just by a little, and also different parts of this like stable diffusion just by a little to increase the performance like massively, right? So again, so one change they have made, as you can see in this image, probably. So this is the image that I want you to see. We'll be adding this refiner block. So in the normal like stable diffusion, we'll be having like only the base models or the unit model, only one unit model, and then the VA decoder and the final image. So that is the like in the normal stable diffusion architecture. But in this case, we have added the refiner model. It's like a new model. We'll be attaching this refiner model to essentially make the like output images of the, or essentially make the images much more high quality. I will cover that, why we'll be needing that. So essentially, again, we'll be taking noise 128 by 128, which is in the training time we'll be using the VAE encoder to actually encode the image representation into some latent space, and that is the latent space, not complete noise. Again, in the training set, so it varies. Like in the inference time, it will be complete noise, but in the training time, it will be like image representation. So that after adding the noise, we'll be doing we'll passing the image through the autoencoder. So VAE encoder, and then we'll be getting the representation. So that will be this noise in the training time. Again, anyway, so what we'll be doing is we'll be taking the prompt, right? We'll be passing both the prompt and the noise, just like in the unit. We'll be having a bunch of resonate connections, right? We'll be passing the prompt through this unit, and we'll be predicting a output, right? Just like in normal unit, we'll be having a unit with bunch of like convolutional 2D transposes and also a bunch of CNNs, right? We'll be having like a combination of both of them in the unit. We'll be having a bunch of resonates. So this is the base model. We have already discussed them. And then we'll be having this output 128 by 128 latent. What we'll be doing is rather than directly passing this through the VI decoder to get this image, we'll be having another model that is again that is trained on images. So that is actually trained on denoising tasks, right? Denoising tasks. So this model is actually trained on denoising tasks on different data sets. So we'll be using this pre-trained model. So we'll be using this pre-trained model to take this output or to take this output of this unit, and we'll be like denoising this output and making the image much more better. So essentially, we'll be adding like two units, which makes the model much more better in terms of generating less noisy images and high quality images. So that is the idea of adding a refiner model, right? So that is the idea. As you can see here, compared to like stable diffusion 1.4, 1.5, or 2.1, 2.1, we have many more parameters. SDXL has many more parameters, 2.6 billion parameters, right? We'll be using, and then we'll also be using like a new text encoder. We'll be using a clip encoder and the open clip VIT BIG encoder. And then the context dimension, we'll be having much bigger one, right? And then also, and one thing we'll be doing is, we'll also be doing one more thing. Like in stable diffusion, while training a stable diffusion model, let's say we have images of belonging to different sizes. So let's say this image has like 1028 by 1028, and maybe this was 128 pixels or 420 pixels, let's say. So essentially, we'll be having images of different sizes. One will be of very high quality and other with like very less quality. like I think in stable diffusion 1.4 and 1.5, right? So in for example, stable diffusion 1.4, 1.5 discarded all images with any size below 512 pixels. So essentially in table in like the like past uh, past versions of stable diffusion, they have discarded all of these images which are lesser than the like a threshold. They said here it is 512 pixels, or alternatively upscale images that are too small, right? Or they either do that, they either discard the images with like lesser quality, or they will just upscale these images that are too small. So that is what they have done. However, depending on desired image resolution, the former method can lead to significant portions of the training data being discarded, right? If we have discarded all of the images with lesser quality, we'll be losing a lot of valuable information that might be good for the model to learn to generate much better images, right? So we'll be not doing that. And also, if we like upscale these images, if we try to upscale these images, then we might produce blurry samples which are blurred out, because upscaling those images mean we'll be doing some average and all that. And of course, they are going to be blurred out, and there will not be any clarity, and the model will actually learn to predict blurry images, which is definitely a very bad sign. So that is why instead, right, we propose to condition the unit model on original image registration, which is trivially available during training. In particular, we provide this image original, that is before any rescaling, height and width of these images as additional conditioning to the model. So essentially what we'll be doing is, in the unit model, right, in the stable diffusion architecture, in the unit model, we'll also be conditioning the image size or image height and width. We'll also be not only taking the prompt, but also the shape of these images as an input, and based on that, we'll actually do that. So that will also be a condition. That will be a condition, and based on that, we'll predict this new image, right? So in particular, we provide the original height and width of this image as an additional condition to the model. C size equal to H original and W original. H is height and W is width. Each component is independently embedded using Fourier feature encoding, and these encodings are concatenated into a single vector that we feed the model by adding it to time step encoding. So essentially, we will be like encoding this I think the sizes, will be encoding the sizes and into a single vector, and we fed into the model, right? So that is the idea. At inference time, a user can then set the desired apparent resolution of this image via the size conditioning, right? While training, we'll do that. While training, we'll just have this input parameter, the condition, which we will send to the model while learning or while modeling different images of different sizes, right? In the inference time, will be the user can, right, we could just input any sizes, and based on that, we'll get the size of we'll get this image, the output image, right? By this, the model can also learn like the relation between the resolution and the image. So it will actually learn resolution dependent image features. The model can learn resolution dependent model image features, which can be leveraged to modify the appearance of an output corresponding to a given prompt. So that is the idea of doing this. And then I think so essentially this is like the training loop that we'll be doing. So we'll be having like width and height. We'll be passing that through R. We'll be resizing that image. We'll be we'll be we'll be reshaping these images, and then yeah, we'll be cropping these images and all that. So that is actually the loop actually, or that is the thing that will be carrying out before this images. And one more thing is, we'll be improving our autoencoder. In the stable diffusion autoencoder, we are going to make very little changes that have proved to work, right? And then so what we'll be doing is we'll be so essentially we'll be calculating like moving average, right? So will be what, so I'm going, while the bulk of the semantic combination is WLDM, we can improve local high frequency details in generated images by improving the autoencoder. To this end, we train the same encoder, so same autoencoder architecture used for the original stable diffusion at larger batch size. So essentially, we'll be doing like images with larger batch sizes. So we'll be adding more batch sizes, and additionally track the weights with an exponential moving average. So essentially, we'll be using something called exponential moving average to update the parameters while training the autoencoder. So while training the autoencoder, we'll be having a bunch of parameters, right? While updating these parameters, right, we'll be following a certain principle. Let's say, so what we're doing is we'll be taking W. So before updating this parameter, we will be taking this W, and essentially we'll have factor called alpha, and based on this, we can just do like W plus 1 minus alpha into, let's say, W of Wi, let's say Wi minus 1. I think the formula is actually not that correct, but with the same intuition and the same goal. So we'll be having this alpha that determines whether we should give more importance to the current weight or the previous weight. So after updating these values, whether to smoothen the training, right? We want the training to be very smooth rather than going like very like very unstable training. We want the training to be much more stable, right? We want the changes to be much more stable in the autoencoder. Let's say we are generating some very good images. We don't want to, like, overhit. So we don't want to, let's say, generate more red pixels and ignore blue pixels. In the next training step, generate more blue pixels and reduce the red pixels. We don't want that, right? We want the training to be stable. We want the autoencoder to be to update its weight very stably. That is why, to increase the stability of our model of the autoencoder, we'll be using this. Also, after updating, we'll essentially be using this alpha parameter to smoothen the training, such that we give like importance to the current weight and also the previous weight before before updation. So that is the idea of this, and I think that's it for this video. And you could actually see like very good thing. So this is the input and this is the output. As you can see, like much more much more, you know in detail, much more details. You could actually figure out much more details here. This is the original image, and this is like very good, right? So they have not used the refiner model here, and they have used the refiner model here. So again, the refiner model, remember the refiner model, right? In the architecture, we'll be adding the refiner model to actually denoise these images and add like more clarity. So without the refiner, we'll be getting these images, and with the refiner, we'll be getting these images, which is actually pretty good in like improvement, I would say. I think that's it. That's it for this paper. And yes, it is a large paper, but I think they just cover like the basics of diffusion models and all that. Yeah. So I think that's it for this video. It was a very good paper, reading this, and also distillation. So thank you for watching. I'll see you in the next one. Thank you. Goodbye.